In Module 5, we're going to consider a significant decision-making tool for data-driven decision-making, hypothesis testing. A quick overview. First, we'll look at the concept of hypothesis testing. Then we'll turn to hypothesis testing when we're testing against a single value. Finally, we'll look at hypothesis testing for when we're comparing the mean or the proportion between two groups. Broadly speaking, hypothesis testing is what we use when we have a decision that will be based on a population parameter, but the population parameter is not observable. So we have to work with a sample statistic instead. So we gather a sample, see whether the sample statistic matches the hypothesis, and then make a conclusion about the population parameter. What makes things a bit complicated, though, is that, as we know from confidence intervals, sample statistics involve a margin of error. So it's not as simple as seeing if the sample mean age is 50. We have to allow for the margin of error around that sample mean. While we'll get more precise than this in a bit, the reality is that if the hypothesis is not strictly true for our sample, but is pretty close, then we won't reject the hypothesis. The question is really just how close is close enough. A point we need to start with, and this is the key to getting hypothesis testing to make sense in a business context. Hypothesis testing is a decision-making tool. For hypothesis testing to be effective in that role, you should start with a default action in mind, but have a willingness to adopt an alternative action if there is sufficiently compelling evidence for it. While this framing isn't necessary for using the tests, it is essential in understanding why we would bother using hypothesis testing at all. In effect, the hypothesis test is how the data could talk you out of the default action. Here's the process for the hypothesis test. First, decide on your actions, a default and an alternative. Second, state your hypotheses, a null hypothesis and an alternate or alternative hypothesis. These will be connected to your actions. Third, choose a level of significance for the test. We'll get into details later. For now, I'll just say that the typical standard is 0.05. From here, there are two approaches we can take. One is the critical value approach. Down this path, you'll find a critical z or t value, calculate a test statistic based on our data, and then either reject the null hypothesis or not reject it and act accordingly. The other approach is the p-value approach. Down this path, we will calculate the test statistic, then the p-value, and then compare the p-value to the level of significance. Based on that comparison, we'll either reject or not reject the null hypothesis and act appropriately. Don't worry if you're a bit lost. We'll go through this in more detail, step by step. Step 1. We need to decide on our actions. Let's make this concrete. Here's a business decision we might need to make. Should we do a detailed review of our operating procedures to prevent excessive downtime? As we know, downtime is expensive, but a review of operating procedures is also expensive. So let's say that, based on our intuition about the situation and our knowledge that a review would be hard to do, we make our default action not undertaking a review. So alternatively, we would undertake the review. So how do we decide which action is which? A few general principles to help here. The default action should be what you would do if you had no new information, or if the information you get is inconclusive. So typically, that will mean maintaining the status quo. So in this case, the status quo is that we keep operating as usual. If that's the plan, then a review of procedures is unnecessary. So I chose a default action of not doing a detailed procedure review. However, there are exceptions. Maybe I'm a particularly proactive manager and really want to review procedures in detail. In that case, I'd need evidence to convince me not to do that. So my default action would be to undertake that detailed review. Neither answer is wrong, it just depends on the specific context. And that's where you need to be the human and assign the actions based on your understanding of that context. Step 2, making hypotheses. So we have our actions. The default is not to review. The alternative is to review. What the hypothesis formation step does is translate these actions into the data that would make them make the most sense. So in this case, the big concern is downtime. So we'll review based on how much downtime there is. Let's say that as long as we average 15 hours per week of downtime or less, we think that's acceptable, so no review is needed. It then follows that if the mean amount of downtime is more than 15 hours a week, we'd want to do the review. So we make the null hypothesis, denoted as H0, that the mean is less than or equal to 15 hours per week of downtime. The alternate hypothesis, which we call H1 or sometimes HA, is the opposite, that the mean is strictly greater than 15 hours of downtime. Notice, we set the hypothesis so that if the null hypothesis is true, the default action is the right choice. If the alternate hypothesis is true, then the alternative action is the right choice. Some general principles here to guide your hypothesis formation. First is that the null hypothesis must include equality as a possibility. So there are three possibilities. One, the mean is exactly equal to some value. We call this a two-tailed test because we're seeing if the sample mean is too big or too small for the null to be true. We're testing two tails of the distribution to check if we have to reject the null. Possibility two, the mean is equal to or greater than some value. We call this a left-tailed test because we're checking if the sample mean is too small, that is, too far left on a number line, for the null to be true. Possibility three, the mean is equal or less than some value. We call this a right-tailed test because we're checking if the sample mean is too large, that is, too far right on a number line. The second principle is that the alternative hypothesis must be the exact opposite of the null. The two must not overlap and must capture every possible value. Finally, that hypothesized value, in our case 15 hours of downtime, should be based on when the default action is certainly best. All of these principles work whether we are testing for means or for proportions. Some additional principles as we wrap up step two. Step two is really all about connecting the action we're going to take and tying it to data. It's what makes the connection between the data and the decision. Just to remind you where we're going with this, in the following steps, what will happen is that if the data is consistent enough with the null hypothesis, then we'll take the default action. If the data is sufficiently inconsistent with the null, then we'll take the alternative action. Naturally, in an ideal world, we'll always make the right choice. However, in reality, we don't have all of the data. We're working with a sample. So we just make the best choice we can, recognizing that our data is limited. In the third step, we select our level of significance. Before I get too deep into the meaning of this, just some values to give context. The standard value is 0.05 or 5%, though sometimes 0.1 and 0.01 are used. Personally, I think you can make a good case for 0.5, but this is quite uncommon in practice. So as we move forward, just keep in mind that the level of significance will typically be about 0.05 or 5%, though it may be in the 1% to 10% range. So what does this 5% mean? For any hypothesis test, there are four possible outcomes. In two outcomes, we make the right choice, either by not rejecting a true null hypothesis or by rejecting a false null hypothesis. However, there are two errors we can make instead. One of those, called a type 1 error, is when we reject a true null hypothesis. The other error is called a type 2 error, and it happens when we fail to reject a false null hypothesis. Using our knowledge of distributions, we can actually choose the probability of committing a type 1 error when the null is true. This probability is what we call the level of significance, or alpha. So that 5% that we chose means that we're saying that if the null hypothesis is true, then we're willing to accept a 5% chance of mistakenly rejecting it, leading to us taking the alternative action when the default action would have been more appropriate. So why don't we want a level of significance of 0? The answer is simple. If you want to make sure that you never reject a true null hypothesis, that's easy to do. Just never reject the null hypothesis. However, this means you'll be committing type 2 errors quite frequently. Put another way, the power of the test, that is the probability of rejecting a false null hypothesis, will be quite low. There's a trade-off then. The higher the level of significance, the more likely we'll commit a type 1 error. But we reduce the odds of a type 2 error. With a very small level of significance, the probability of a type 1 error is quite small, but the probability of a type 2 error is fairly high. This trade-off between the probability of type 1 and type 2 errors is what should drive our choice of the level of significance. If we commit a type 1 error, we'll be taking the alternative action when the default was the right choice. If we commit a type 2 error, we'll take the default action when the alternative was the right choice. In our example, a type 1 error would be performing a review of procedures when that review isn't really necessary. A type 2 error would be not performing the review when it would have been good to do. So then, when setting the level of significance, we have to compare the relative severity of type 1 and type 2 errors. At the standard level of 0.05, a type 1 error should be deemed to be a bit worse than a type 2 error. In our case, we've decided the expense of an unnecessary review is worse than not performing a review, even if that would have been somewhat helpful. If, though, a type 1 error would be particularly bad when compared to a type 2 error, then we need to set the level of significance very low, 0.01 or even lower at times. If, on the other hand, a type 2 error that is pretty bad relative to a type 1 error, that calls for a higher level of significance, maybe 0.1, or in the extreme case should lead us to switch our default and alternative actions. After all, if it's really, really bad for us not to review procedures if we need to, then we should just plan to review them, unless we gather strong evidence that it's not necessary. In short, by the design of hypothesis testing, the default action is favored. So we need to make sure that it's not going to be disastrous. Example from the world of pharmaceuticals. Generally speaking, the FDA operates with the default action of not approving the drug. The alternate action is approval. What that means is that the FDA requires fairly strong evidence of safety and effectiveness before they'll approve a drug. This is implicitly assuming that it's worse to approve an unsafe or ineffective drug than to deny approval of a safe and effective drug. Once we have completed step 3, we now have to choose which approach we want to use, the critical value approach or the p-value approach. The critical value approach asks us to calculate the z or t value from the sample and compare to a critical value. This option has the benefit of using concepts we've seen before. Z and t are nothing new, and this approach overlaps a lot with the work we did on confidence intervals. The second option is the p-value approach. This asks us to calculate the true probability that we're committing a type 1 error if we reject the null hypothesis, and then compare that to our level of significance. This has the benefit of being easier to interpret. Both of these approaches give the same result, and so there is no obvious superiority of one over the other, especially once you get some practice. Let's start with the critical value approach. If we follow this approach, the next step is to find our critical z or t value based on the chosen level of significance. Here the standards are the same as with confidence intervals. In general, if the sample is large enough, we use a normal distribution. If it isn't, we'll use student's t-distribution. Either way, you can find the critical value by using a t-table and reading off the row for the degrees of freedom, or the z row if you're using the normal distribution, and then the column for the chosen level of significance. We'll assume the sample is large enough that z, or the normal distribution, is what we can use. When we determine the distribution, we have to determine if we're going to do a one-tailed or two-tailed test based on step 2. The rule is that if your null hypothesis includes an inequality, then we have a one-tailed test. If the null requires equality, then we have a two-tailed test. In our example, we're doing a one-tailed test. The null includes both equal to and less than 15 hours of downtime per week. For a one-tailed test with a level of significance of 0.05, the critical z value is 1.645. So what does this 1.645 mean? This step is really a connecting step between the previous, when we chose our level of significance, and the next, when we'll convert our data into a z-value. What the critical value does is provide a connection between this 0.05 level of significance and the z-value we're going to calculate. So where we are heading is, if the calculated z-value is past the critical, then the probability of wrongly rejecting the null is low enough that we should reject. So here's the visual to help you get an idea of what's happening. What this distribution shows is the probability of getting a sample statistic in a particular range, given that the null hypothesis is true, where the null would be in the center of this diagram. So as long as our sample statistic is in the center range, then we're close enough to the null to say that it might be true. So we'll act as if it is true. However, if we're in the red regions, then the odds of getting these statistics if the null is true is really, really low. So the null is probably not true, and we can reject it with only a small chance of committing a type 1 error. The critical value is just the cutoff between the non-rejection and rejection regions. In the case of one-tailed tests, the entire rejection region is on one side, whichever side is not consistent with the null hypothesis. Now, there are some adjustments we have to make if we're drawing from a t-table. The t-table always gives a positive critical value, but that's not appropriate for some tests. For right-tailed tests, no change is needed. For a left-tailed test, where we reject if values are very low, we need to add a negative sign. We will only reject if values are too low. For a two-tailed test, we add a plus and minus sign, because we'd reject if the test statistic is either too low, that is to say too negative, or too high, that is too positive. You can use Excel functions to find critical values if you wish. I'm not going to read these off, but feel free to pause, copy these down if you need them. The next step in the critical value approach is to compare the critical z or t value to the actual z or t statistic. Conceptually, the z or t statistic is the number of standard errors the sample value is from the hypothesized value. So you calculate it by taking the sample value, subtracting the hypothesized value, and then dividing by the standard error. That is, the sample standard deviation divided by the square root of the sample size. In Excel, you can use these functions to get the calculated z. Pause if you need to get the formulas. General observations about this. The previous formula was for a mean hypothesis test. Conceptually, there's no difference between this and the test for a proportion. You just have to adjust to the standard error for proportions. Now, I will note there is some disagreement in the calculation of this. Since the standard error for proportions depends on the proportion itself, it's not immediately obvious whether we should use the sample proportion or the hypothesized proportion. Personally, I side with sample, simply under the view that the standard deviation that we use for means is based on the sample. So it seems reasonable that the sample proportion would be used in this case. The final step in the critical value approach is to either reject the null or not, and then take appropriate action. In our example, we found a z-critical of 1.645, and a z-test statistic comes to 4.66, let's say. So for this right-tailed test, we would reject if the test statistic is greater than the critical value. And it is. So we reject the null hypothesis. This means then that we have evidence that our mean downtime is significantly higher than 15 hours per week. So we should review our processes. Here we lay out the general principles. In short, we reject the null whenever the test statistic is, first, inconsistent with the null hypothesis, and second, sufficiently extreme. That is to say, it's more extreme than the critical value. In a right-tailed test, that means having a very high positive z. In a left-tailed test, that means having a very negative z. In two-tailed tests, it means having a z that has a value very far away from 0, regardless of whether it's positive or negative. One other note. We never say that we accept the null hypothesis, rather we do not reject or fail to reject it. The main reason for this comes from two-tailed tests. Odds are you'll never have a sample mean that exactly matches your hypothesized mean. So we can't say that the sample supports the hypothesized mean as true. What we can say is the sample mean is close enough to the hypothesized mean that we can't say for sure that it's wrong. Now let's turn to the p-value approach. First, a little comparison. The critical value approach takes the philosophy of identifying the rejection region, finding critical values to define that region, and then determining if the test statistic falls in that region. With the p-value approach, what we're doing is calculating what the probability is of getting a sample statistic at least as extreme as we observe, if the null hypothesis is actually true. Then we determine whether this is low enough to reject the null hypothesis as false. In effect, if we have a sample that is way off of the hypothesis, then what we're saying is that if the null were true, then this sample is very unlikely to happen. So the null is probably not true. Note, the two should give the same results, as long as our critical z is chosen in a way that is consistent with our level of significance. So following the p-value approach, we first calculate the test statistic. This is exactly the same calculation we used for the critical value approach, so I'm not going to comment much on this. The next step is to calculate the p-value. For this, we can use a computer. There are a number of forms of Excel formulas that would work for this. In our example, we need the form for a right-tailed test, which is the formula you see on the screen. Simply replace z-test with the value you calculated in the previous step. Before I move on, a quick note on the norm.dist function and what it does. This returns the probability of getting a value less than the z-test in a standard normal distribution, with a mean of 0 and a standard deviation of 1. That's why the 0 and 1 are in the function. It indicates the mean of 0, standard deviation of 1. The true in the function tells it to return the cumulative probability up to that value of z-test, rather than just the height of the probability density function at that value. So in effect, this is calculating the probability of getting a value less than the value of the z-test. What we want for a right-tailed test, though, is the probability of getting a value greater than the value of the z-test. So we take 1 minus the calculated value to figure out what probability is left for the right tail. To generalize, here are the formulas you would need for the different types of tests you may do. Pause and jot these down if you think you're going to need them. Next step is to compare the calculated p-value with the level of significance. In our example, the calculated p-value is 1.58 times 10 to the negative 6th power. That is to say, we'd have a decimal place followed by 5 zeros and then 158. This is definitely smaller than the level of significance of 0.05. While technically the calculated p-value is the probability of getting a result at least this extreme if the null hypothesis is true, a good way to think of it is that the p-value captures how consistent with the hypotheses the data we have is. A p-value of exactly 0 means that the data is completely inconsistent with the hypothesis, while a p-value of 1 in a two-tailed test indicates that the data is completely consistent with the null hypothesis. Having done the comparison, we reach our conclusion. We should reject the null. In the p-value approach, we compare the p-value to that level of significance to make this decision. If the p-value is less than the level of significance, that tells us the data is just too inconsistent with the null. So our odds of being wrong when we reject it are pretty low. So we should reject the null, which in this case means we should review our operating processes. Some quick general notes. Both approaches work and give the same conclusion. So what you want to do is a matter of taste. Traditionally, the critical value approach was fairly common. The usual critical values were well known. The test statistics are pretty easy to calculate. However, more recently, there has been more of a move in favor of p-values, as the widespread availability of computers have allowed us to overcome the challenges of calculating p-values. And many people, myself included, find p-values a bit easier to interpret. One more point. If we run a two-tailed test and reject the null, it is statistically valid to not only say that the population mean isn't what we thought it was, but to indicate the direction of the error. The reason for this comes down to how p-values are calculated. Basically, the p-value for a two-tailed test is twice as large as for a one-tailed test, which means that if it's small enough to reject the null, then the appropriate one-tailed test would also have rejected the null. Another important note, we use this term significance, but it has a very specific meaning. When we say the result is statistically significant, what we mean is just that there's good evidence that reality is not the same as what was hypothesized. This is not the same as saying the difference is important or large. For example, maybe we have evidence that the downtime is statistically significantly higher than 15 hours per week. This might mean it's 30 hours per week, a huge difference. Or it might mean that it's 15.3 hours per week, but their evidence is really strong. Either way, our evidence is strong enough to say that it's almost certainly higher than 15, but there is certainly a practical difference between the two. I wouldn't be so worried about a 15.3 hour per week downtime as opposed to a 30 hour per week downtime. Similarly, statistically insignificant just means we don't have good evidence that the reality is different from the null. So it might be that the evidence we have suggests an enormous difference, say 30 hours per week versus the 15, but that the quality and consistency of that evidence is not good enough for us to have much confidence the difference is real, rather than just a result of the randomness that's built into every sample. So a quick note then about the proper and improper use of hypothesis testing. The American Statistical Association put out a statement about p-values a few years ago, and I highly recommend reading it. In short, the ASA was concerned that what I'm going to call p-value extremism had started to cause problems. So here are some of my thoughts based on reflecting on that statement. These should not be taken as the statement itself. I actually disagree with it on certain points here. First, we know that scientists often use hypothesis testing techniques, with the null hypotheses typically being that no relationship exists between a pair of variables, say atmospheric CO2 levels and global temperature. The alternative hypothesis then is that the relationship does exist. In this world, significance extremism becomes very misleading. A p-value of 0.049 is less than 0.05, so we'd reject the null and conclude that this relationship must exist. However, if the p-value were just a tiny bit higher, say 0.051, we'd not reject the null and conclude that the relationship doesn't exist. This is naturally a little bit silly. That small a difference shouldn't totally reverse our conclusions. This is where I would suggest that the proper use of hypothesis testing is for decision making much more than for science. After all, when we make decisions, we have to do something, even if that something is just maintaining the status quo. This implies that some kind of bright line test is needed. That is, we have some criterion by which we decide to take one course of action versus another. In contrast, pure science, which seeks simply to understand the world, doesn't require us to have such a test. So hypothesis testing isn't really necessary. We can use other methods. For example, Bayesian methods allow us to talk about the consistency of models with underlying data without having to take the extreme position of entirely rejecting a model. We can simply rate it as less likely based on the information we have. That said, even in a decision-making context, it is probably unwise to use a hypothesis test blindly. After all, such tests can be influenced in unpredictable ways if outliers sneak into our samples, for example. So it's always a good idea to check the underlying data. And as an analyst, to provide the data itself, perhaps in a few visualizations, along with your analysis of it. Just a quick note about Excel before we turn to looking at hypothesis testing for comparisons. In short, Excel isn't actually built very well for single-valued hypothesis testing, but we can use the built-in functions and templates to get the work done. Excel, it turns out, is much better built for doing comparisons between samples, which is good since this is fundamentally more difficult to do. A lot of the time, if we make a decision, we need to compare two populations, and therefore two different samples. So, for example, we might want to compare the effectiveness of a particular ad across different demographics to decide if we should use the same ad for everyone or have more targeted ads for different demographics. Or perhaps we want to see if one plant's operations are meeting the standards we find being met in other plants. So consider this question, which we saw in a previous assignment. Does the manager of a particular plant deserve a raise? In gathering evidence, we'd ask whether their plant is more productive than their peer plants. In answering this question, we will formulate the hypothesis as a two-tailed test. That is, the null is that the mean for the two populations is the same. The alternative is that they are not the same. So rather than testing against a particular value, we're going to be comparing two estimates that come from two samples drawn from these two populations. What we need then is a method that acknowledges that both sides of this equation are estimates. Now, it might be tempting to do something like this, to just calculate the mean for one of the samples and then test the other sample against the mean we calculated. For example, in our plant manager example, maybe the sample mean for the peer plants is 125,000 units per month. So we can just test plant number one's mean against 125,000, right? Well, no. Take a moment to see if you can figure out why. Take a pause and think about it. The fundamental problem is this. Formulated this way, what we'll find is whether the production of plant 1 is significantly more than 125,000. What we won't find is whether plant 1 is significantly more productive than the other plants. To answer that last question, we need to acknowledge the uncertainty of the 125,000 estimate. In doing these kinds of comparisons, we have four techniques. Three of them are for comparing means and one for comparing proportions. The three for comparing means exist in a hierarchy, as listed here. The top of the list, matched pairs, is the most powerful technique, but the situations in which you can use it are inherently limited. The last, unpaired with unequal variance, is a weaker technique. That is, it involves greater levels of uncertainty, and therefore a smaller likelihood of rejecting the null for a given set of data, but it's much more widely applicable. So let's start with paired means, also known as matched pairs. In this technique, you have to have each observation in one sample paired with an observation in the other sample, typically based on some kind of what I like to call a natural pairing. The most obvious case for this would be before and after types of comparisons. So if we're trying to figure out whether a particular diet or exercise program works for a particular measurable goal, we can gather data on weight or strength or running speed and so on prior to the program, and then gather the same data for the same people afterward. The fact that it's the same person for the before and after data creates a natural pairing between the data points. You can do the same thing with looking at things like test performance. On a business level, we can evaluate productivity before and after a training program. Using the p-value method, you can use the Excel function t.test. For this function, you have four inputs. The sample data sets are the first two inputs, then how many tails your test involves, that's either one or two, and finally the type of test you're performing. In our case, that would be 1 indicating a paired test. The output from this function is the p-value, which we can then compare with the level of significance as we previously described. So remember, a low p-value indicates the data is not consistent with the null. So if the p-value is low enough, we reject the null hypothesis. One important note, the one-tailed test in this function assumes that you're not stupid. That is, it assumes you already checked the means. If the means were consistent with the null hypothesis, that is, whichever null you expect to be higher is actually higher, then no calculations would be necessary. Excel then chooses the right-tailed or left-tailed test based on the assumption that the raw data is pushing us toward the alternative hypothesis. So it's just trying to tell us whether the data is strong enough for us to reject the null and go with the alternative. Another limitation is in data analysis, where the three test types are all available. I prefer this way because it gives us more information. It also does not require committing to a one or two-tailed test. The output for both would be reported. So here's how we implement this. In the input box, we tell where the data is. Then you can have a proposed difference other than 0 if you wish, something t-test will not do. And you can also set your alpha, that is the level of significance. Then here's the output you get. At the top, we have the means for each sample, so we can see which is higher in the sample. Toward the bottom, we can observe the calculated t-statistic, which we can compare to critical values, which it provides if we want to use that method, and also the p-values and critical values for both the one-tailed test and the two-tailed test, right, are provided to us. These two methods, that is t.test and the data analysis approach, I prefer the data analysis approach. It's more flexible, it allows us to hypothesize a difference, and also it gives us much more detailed output. Now at this point, I've not really told you how this matched pairs or paired means test works. It's actually fairly simple. Rather than looking at the difference of the means, this is looking at the mean of the differences. So in a before and after kind of scenario, for example, the algorithm doesn't look at the data before and the after data. Rather, it looks at the change between the two. So we have just one data series with all of the changes in it. And then we can apply our standard techniques with the hypothesis that that mean is going to be equal to 0. Everything else follows from what we did previously with the single valued test. Just the mean of all of these differences is equal to 0. It would be our null hypothesis. The mean is not equal to 0 would be the alternate, and then we use all of the standard calculations. All of this is what's happening under the hood in Excel here. So, for example, when we're looking at scores on, say, a test 1 and test 2 for a particular class, the algorithm is just going to look at the changes for each student, thus making one data series out of what looks like 2. Having a single data series reduces the amount of uncertainty involved, which is what makes this such a very strong test. So, as a general rule, it's a good idea to use matched pairs whenever you can. But that's going to require both equal sample sizes and some logical way of pairing the two samples. Sometimes this is obvious. Before and after cases would be the most obvious case. But other times you might be able to force it. For example, if you find two cities that are demographically very similar, you can run different ads in them and then compare using matched pairs. However, in this case, the strength of the test is only as good as the strength of the pairing. Generally, if you're going to use matched pairs, really to get it to work, you have to decide prior to gathering the data, just to ensure that the pairs actually exist. The second type of test is if you have unpaired data, but with equal variances for each sample. A good example of this would be if we were comparing one class's scores on a test with another class's score on that same test. There isn't an obvious pairing between the students in each class. In fact, they might be different sizes. If we have different sample sizes, there's no way to pair them up. However, the test is exactly the same, so it's reasonable that the variances should be similar for the two classes. I'm not going to go into too much detail here, since this is something Excel can really handle very easily. The basic idea, though, is that when they're not paired, we can't just pull that paired trick of looking at a single set of changes rather than looking at the two separate series. And that second series is going to add some additional uncertainty, which ends up in practice increasing our p-value. That is, the additional uncertainties make it harder to say that a given set of data is inconsistent with a particular null hypothesis. However, the good news here is that because the variances for the two series are assumed to be equal, we can at least combine the two data sets to calculate the variance. This allows for less uncertainty than if we had unequal variances for the two samples. This slide simply discusses how we can combine the sample standard deviations into a pooled standard error. Don't worry about the details here. If you're curious, feel free to take a look. Now, what about the hard case, with unpaired data with unequal variances? The question about the difference between plants probably falls into this category. There's no obvious pairing, since we're looking at one plant providing one sample and a set of plants providing the other sample, And the plants logically may have different variances based on differences in local management strategies, climate, and so on. What this means then is that we have an additional variance that has to be estimated, which creates an additional source of uncertainty. I'm not going to go into all of the mathematical details here, just let Excel do the work for you, but rather let's focus on the intuition. Because there's more uncertainty involved, since more is being estimated, we're going to have to end up with higher p-values. That is, it's going to be harder to say that the data is definitely not consistent with the null. So, if you have a given set of data for which matched pairs is possible, you'll have this ordering of p-values. The p-value for the matched pairs method will be the lowest, followed by if we use the equal variance method, and finally the p-value for unequal variances is the highest. This means that the matched pairs method is the most likely to allow us to reject the null hypothesis, reflecting the fact that there is less uncertainty involved in that style of test. Just to summarize then, the different sources of uncertainty. With the paired means method, we have a single sample of differences or changes. For that sample, we estimate the mean and the variance or standard deviation. So there will be two estimates involved. With unpaired data with equal variance, we now have two separate means plus a single variance. That's three estimates. With unpaired with the unequal variance, we end up with four estimates, the mean and the variance for each sample. So a quick summary then of these methods. We know that if we have more sources of uncertainty, we'll get larger standard errors in smaller t-statistics. This makes it harder for us to reject a null hypothesis. So we put the test in a hierarchy. Paired means the best when it's possible, followed by unpaired but with equal variance, and then unpaired with unequal variance is the last resort. This allows us to avoid introducing uncertainty into the test unless it's necessary, so we don't water down the information we have. Now let's turn to how we handle proportions. The bad news is that Excel is not great at dealing with proportions, so this is a case where we're going to have to do more of the work in putting in formulas and the like. So now there is a cheat. If you want to, you can use your data to create two samples, where in each sample you'd show each observation as either a 1 if it's a success and a 0 if it's a failure. Then you can use the unpaired equal variances technique to basically replicate what I'm doing here. However, there are two issues. The first is that as long as we have 5 successes and 5 failures in each of our samples, a normal distribution would be appropriate for proportions. But Excel just assumes a t-distribution all the time. Now, if your total sample size for either sample is under 30, this can create a pretty big difference between the t and the normal distributions used for that test, and that can impact your results. Now, if the sample size is really big, like the example we're going to look at here in a minute, simply setting up the spreadsheet to do this can be a big challenge. Or in a truly big data context, there just aren't enough rows allowed by Excel to make it work. So I'm going to show the mathematical formulas you need that will allow you to build a template that can then be used for solving these problems. The good news is once you build this template, you can always just reuse it in any problem you find. Let's think about an example. A typical case of this would be A/B testing for online ads. The basic idea is that we have two ads, we call them A and B, and users are randomly selected to see one ad or the other. Then we track both the number of views for the ad and the number of clicks for each ad. We want to know if one ad is better than the other in terms of being more effective at turning views into clicks. This would involve comparing the click-through rate, that is the proportion of viewers that do click on that ad. So we're comparing proportions. So how do we do this? First, we need to state our hypothesis. In this case, we don't have a default ad we'd want to run. We just want to know if the two are different. So we'll use a two-tailed test where the null hypothesis is that the proportions for the two ads are equal. And the alternative is that they're not equal. If the alternative ends up being preferred, we know that the test is powerful enough to establish not just the existence of a difference, but also the direction of the difference, so we can figure out which of the ads is in fact more effective at getting a greater level of click-throughs. For our second step, we compute the pooled proportion. That is what the proportion is overall. This means we combine the number of successes, in this case clicks, and the number of observations, in this case views, and then calculate the proportion using those combined totals. In the third step, we calculate the pooled standard error. This is very similar to the standard error for proportions in general. The only complication is that we have two different samples, each with their own sample size. So rather than dividing by a single n, we multiply by the sum of 1 divided by n1 plus 1 divided by n2. Once we have the standard error, we can calculate the z-statistic by taking the difference between the proportions and then dividing by that pooled standard error. Then we compare the result to a critical value and we can draw our conclusion. In this case, it turns out the z-value, that is the test statistic, is 0.895, which is certainly less in absolute value than our typical two-tailed critical value of 1.96 if we have a 5% or 0.05 level of significance. It's in fact even less than the critical value if we have a higher level of significance of 0.1. So we cannot reject the null. There's not sufficient evidence of a difference in click-through rates between these ads for us to use this to prefer one over the other. And one last step, which is optional but nice if you want to use the p-value approach, is to use the formulas we previously discussed for calculating p-values to calculate the p-values. So we can then compare directly with the level of significance. All of these are stated here right on the screen, so feel free to use these as you wish. So what are the takeaways for this? First, there are a number of human tasks that you must do, which we can divide into two categories. First, when formalizing the problem, you have to decide what the actions are and which action is the default. You have to decide what the relevant hypotheses are. That is, what is the null hypothesis that would justify the default action? What is the alternative hypothesis which would justify the alternative action? What should the level of significance be in light of the seriousness of the consequences of committing a type 1 versus a type 2 error? Second, when interpreting the results, you have to decide if the null gets rejected or not and what action must be taken in light of the results. On the other hand, statistical software can be used to do the calculations for us. This is what computers are good at. So let the computer be the computer. It's your job to be the human.